So welcome to today's Gold seminar, and today I can introduce Fioravantes, who will talk about maximum locally irregular induced subgraphs.
Thank you. Yes, the title is Maximum Locally Irregular Induced Subgraphs. This is a work that is done in collaboration with Nikolaos Melisinos and Theophilus Triomatis, two very good friends of mine, which was presented recently at the SWOT 2022 conference. Okay, a bit about me, just because I'm new here. I'm a new postdoc that I joined last month, but you can expect to see me more from now on. And I'm sorry if the affiliation is wrong. I improvised something. I hope it's okay. So let's start. And we start by considering a large set of problems in which the problem we studied falls into, which is called the induced subgraph with property P. And it appears already in a very nice book, which I hope people know. So what the input is, we are given a graph and a positive integer, and we are asked whether or not we can find an induced subgraph that verifies a required property P and has at least k vertices. In other words, find the largest, the optimization version would be to find the largest induced subgraph that verifies the property P. Property P, it's very abstract. It could be something like all the vertices of the remaining graph have odd degree, or the graph is deregular, let's say. These are some examples of properties that have been studied before. Now, a little bit of a reminder, a graph is regular if all of its vertices have the same degrees. Here you see three examples of regular graphs. And as is natural, whenever we have a notion, we also like the opposite notion to be well-defined and studied. And in this case, what could be the opposite of regular graphs? Not just that they are not regular, the opposite. Well, it would be that every graph, every vertex has a different degree. Can somebody give me an example of an irregular graph? That's what we call an irregular graph. So I want all the degrees to be different.
K1.
You found it. Yes, it's only this one. There's no other one, and it's a very simple argument just by pigeonhole. And if you want, there is even written as a proof at some point. So this leads to the idea of introducing different notions of irregularity. One of which is the one that we are interested in, the one of local irregularity, in which we say that a graph is locally irregular if any two adjacent vertices have different degrees. I give you, these graphs do exist, thankfully. I give you some examples. I think you can very easily verify that these are indeed locally irregular. Maybe this one is a bit weirder. And the reason why we focus on these graphs, well, they are kind of important in the what is known as the 1, 2, 3 conjecture. I will not spend some more time on that. If you want me to talk about it, come and talk to me. Basically, it's a way to find proper colorings by putting weights on the edges of a graph. Okay, so that's the problem we introduced. Find the largest locally regular induced subgraph of a given graph. Okay. An example. Let's take this graph. First of all, is it locally irregular? No. I have these two vertices. They are adjacent, and both of them are of degree 3. So I do need to delete at least one vertex, right? I'm searching for induced subgraphs. And indeed, this is a very neat observation. Whenever we have two vertices that are exactly like that. They are adjacent and they have the same degree. We know that we will need to delete at least one vertex in their closed neighborhood, the red vertices. So let's find a solution. Okay, if we delete these two, we do have a solution which leaves us with a graph of order 6. Can we do better? Yes, we can only delete this one. And this is locally irregular. And we know it is optimal because we do know that we need at least one deletion. So far, so good, easy stuff. But this observation will be useful throughout. So keep it in mind. A bit of terminology. We say that, I mean, the problem makes more sense, at least to me, to be thought of as find the minimum number of vertices that have to be deleted. I think it's easier to follow the problem like that. So we define an irregulator as a set of vertices where if we remove them, what remains is locally irregular. And the order of a minimum irregulator of a graph is what we denote by I of G. Our results. We solved the problem for some simple families of graphs, path, cycles, trees, complete and complete bipartite graphs. To be fair, most of these are trivial. The only one that is a bit tricky are trees. And then we were struggling a lot to find solutions for other families. And that's when we started observing that the problem is NP-hard for subcubic planar bipartite graphs and cubic bipartite graphs, cubic being 3 regular. Okay, these are quite restricted families of graphs. Let's try to approximate it. We do have a proof that we cannot have a good approximation in polynomial time. Okay, what remains to be done? Parameterized complexity. Let's find FPT algorithms. Okay, we did find 2. One which has a parameter the size of the solution in the maximum degree, plus the maximum degree. And the other one which has the tree width plus the maximum degree. And we also showed that if we only consider the size of the solution or the tree width, the problem is not FPT. So let's, usually I skip this part because I repeat it's trivial, but I think that for the purpose of this seminar, it might be a good introduction, a simple result. Let's see how we did the paths. We basically show these values for a path of length n. The idea is we do induction and every 4 vertices, we delete 1 vertex. Because I know that these two have the same degree and I need to delete at least 1 vertex in their closed neighborhood. So I do it. The +1 up there is a bit evil because if we do this, then for some values, the ones that are congruent to 2 modulo 4, we're going to have a K2 that will remain. And this requires an extra deletion because these two have the same degree. This is evil for a reason which will become clear in a bit. For the moment, okay, cycles are exactly the same. I do know that I do need to do 1 delete, and then I have a path. So I do exactly as previously. Now, why the +1 is evil? Basically because of that. It was one of the first examples we observed where increasing the size of the graph decreased the number of deletions we had to do, which is a very bad property for if we want to start building solutions and keep expanding them. This is known as a hereditary property in the context of largest induced subgraph with property P. And the fact that it is not respected, it means that our problem is not hereditary. Okay, so I will now show you the proof of our inapproximability result, because I find it very nice. So what we showed was that for any bipartite graph, it is NP-hard to approximate the optimal solution within this factor up there. And this we achieved through what is known as a gap-producing reduction, where basically we create an instance which it is NP hard to decide if the optimal solution is smaller than a value or very, very, very larger than a, no, or larger than a way bigger value. So we don't know where our graph falls. Now, the reduction is from a problem known as two-balanced SAT. It's a variation of SAT, where each variable appears 4 times, 2 as positive and 2 as negative. I always find it's easier to understand with the figure. So I have my variables here. Each one appears as a positive and as a negative. And since it appears in 2 clauses, each one has a degree 2 here. And it's a variation of 3 sats, so 3 variables per clause. Remember this nu is the number of pairs of variables. So let's see our construction. We start with this. We add this nice gadget, and we add many such gadgets, that many. And then for the clauses, we add these simple gadgets, but then we also add that many, the same many copies of all the clauses. And I know that right now you are maybe wondering why. I will try to convince you a bit about how this proof works. Let's say that the formula is satisfied and show that the solution, the optimal solution, will be of size at most nu. Now, since the formula is satisfied, I know that for some values, for us, a satisfying assignment of the formula, at least one of these 2 is going to be put at true. So what do? I delete it. Now, observe that since I deleted it, all this part here is okay. It's locally irregular. There is no problem between this and this, this and this, and this and that. The degree of this guy is huge. We don't care. And the same with this part. So this part of the graph is okay. Now, from this part of the graph, since the formula was satisfying, it means that each clause had at least one appearance of the deleted vertex, which means that their degree decreased by at least once. Their neighbor is of degree 4. So this is a valid solution. This is indeed a locally irregular graph. And that's the easy part. Now, let's suppose now that the formula is not satisfied. And let's try to find an irregulator of this monstrosity. First of all, we can see here, this is of degree 4, and this is also of degree 4. So I need to delete something here. Can we do this, which means that basically I need to delete at least one of these 2. Or this guy. If I delete this guy, I have that many copies of these K2s, and I need to delete this many vertices. So this is not a good choice. Can I delete only one? Can I delete both of them? Well, if I delete both of them, I have this is of degree 2, this is of degree 2. I have to do that many deletions. Lost. Can I delete only one of them? I could, but the problem is that no matter which combination I choose for them, which deletes only one, it will not be a satisfying assignment for the clauses, since the formula is not satisfied. Meaning that at least one clause will remain like that, and we have this many copies of that clause that remain like that. So any possible solution, if the formula is not satisfied, is going to be of size more than that. I hope this was not too hand-proofing. Let me continue. So we cannot, I did not give you the complexity proofs, but many of our arguments are similar to what I showed you. So you basically get the idea. Let's go to something more interesting. Let's see our positive results that we have. The first one is an FPT algorithm with parameterized by the size of the solution. And this is rather straightforward. It's basically based on this argument that I gave you before. I know that I need to delete at least one of these vertices. So I do branch and bound. I find 2 vertices that are problematic, and I try their neighborhood. And for each one of the neighborhood, I explore, and if I find something, I keep it, and if I don't find something, I throw it away. Also, with the tree width, it's your basic dynamic programming on the graphs of bounded tree width. I don't think this is very interesting to explain how this is done. What is interesting, however, is that we spent a lot of time trying to get rid of the maximum degree, because it can be of big O of n, and we did not like this at all. And so the question that we tried to answer was, can we find an FPT algorithm which does not have this maximum degree inside? And the answer, unfortunately, is no for both cases that we considered. So if the problem is parameterized by the size of the solution, it is W2 hard. And if it, and this is a reduction from the dominating set. And if it's parameterized by the tree width, only the tree width, well, it is W1 hard. This is from the list coloring. This is a reduction from the list coloring. List coloring, recall, we have a graph. For each vertex, we have a list of allowed colors. And we need to find the proper coloring of the vertices of this graph, respecting the list of allowed colors. So here, for example, this is a good coloring. This is blue, and blue is in the list of this vertex, and so on. This is red, red is in the list. And the reduction is from this problem. In particular, we just show the direction which states that if the irregulator is of size, the optimal irregulator is of k times n, then the list coloring is a yes instance. The k is the largest color that appears in the list coloring problem. Okay. Again, a bit of a nice graph. Okay, so the black vertex in the middle corresponds to, is any vertex of the original graph. So on every vertex of the original graph, we attach a lot of gadgets, basically. Now, let me try to explain a bit. Here we add M, what we call horn gadgets. This M serves two purposes. First of all, it's very big, very big. Second of all, it serves to make if I look only the vertices of the original graph after the addition of the gadgets, I want it to be a regular graph. I want all of them to have the same degree. So if so I add these, I will explain how. I add this, I will explain how. And in the end, I want that the degree of this vertex here is the same as of its neighbors in the original graph. So I add horn gadgets to achieve that. Now, what do we want, really want the horn gadgets? Well, we don't want to delete U prime. And if I delete U prime, I will need to add to delete another M vertices. So I do not delete U prime, and if I want a solution which is of size Kn, equal to Kn. Okay. Now, maybe you get a bit the intuition. The idea okay, you said that. The idea basically is to build a correlation between the degree of the vertices like U prime and the color that they will get from the list coloring problem. So what I do with the forbidden color gadgets, I basically, if color 5 is forbidden for this vertex, I put a star here, which is of degree 5, meaning that the degree of this vertex here should be different than 5 in the end. So here, I only put the degrees or the colors that are not allowed for the corresponding vertex. And then I needed to find a solution, because this is not locally irregular. These two vertices have the same degree. But these gadgets are very nice because they allow me, I have a freedom, I have a choice. Either I delete a leaf and I turn this into a locally irregular graph, or I delete this vertex here. And this is important because if I delete this vertex here, or this, I also change the degree of U prime. So basically, if I can find a solution which deletes exactly k vertices in these k degree gadgets, I also have a yes instance for my list coloring where the color of this vertex is going to be the degree of this vertex in this graph. Now, some simple observations. The graph that we built, it was basically a graph plus some trees. This is very practical because the tree width does not change, which is usually a technical part in these kind of proofs. We have added a polynomial number of vertices, list coloring is W hard, and we get everything we have for list coloring. We get them directly for our problem. In particular, under the ETH, we know that there can be no such algorithm for list coloring. We have this for our problem as well. Okay, so to sum up, we studied a problem which proved to be harder than what we initially thought it would be. There are some easy cases where we found not polynomial algorithms, like exact values, path cycles, complete and complete bipartite graphs. The trees that I have there, I'm cheating, it's the tree width algorithm. But since the complexity of our algorithm, okay, tree width of a tree is 1, so we don't, it's still polynomial. Okay, yes, that's it. Here, if this is 1, it's a polynomial. We are okay. We do have a parameterized algorithm for the size of the solution plus maximum degree and tree width plus maximum degree, but we cannot have an FPT algorithm if we only consider size of the solution or tree width. Now, obvious question, can you give me a parameter for which this problem might be in FPT? I would be very happy if you could. I see Dushan is saying yes, yes, I can. Okay. Our inapproximability proof is for bipartite graphs. We are fairly certain that perhaps for cubic bipartite graphs, there could be some approximation that could happen. And finally, there are some variations which we would be interested by. The chief among them being dropping the induced subgraph. So just find the largest subgraph that is locally irregular. In other terms, I also allow you to delete some edges if you want. And that's it. Thank you.
Questions? Okay, so you said that it's just a way of thinking about it, that you are searching for the minimum irregulator of your graph. But is anything known about the complexity, like with the dual parameter? That means the actual size of the graph that I'm searching for.
I mean, as I understand this problem, they are exactly okay. So you are asking, if I understand what you're asking, consider the parameterized maybe complexity of this thing, but not with as a parameter what I remove, but what stays.
Yes.
That was exactly a question a proposal that was given to us in SWAT. Okay. We tried it a bit. The main problem we have is that is exactly that if I have a solution, a subset of the solution is not a solution anymore.
Okay.
So you see what I mean?
Yeah.
So it's not as immediate, and we kind of think that it's not enough, unfortunately. I'm not sure I convinced you, but
yeah.
But that's yes, that's the second time somebody proposes this, and
yet another possible parameter, like just the size of solution, the number of things you have to delete together with tree. Is that
the number of vertices I have to delete only
together with the tree?
Ah!
That sounds
Hmm.
like the question
Hmm.
from this slide.
Okay. Okay, this is the first time somebody proposes. I have no idea. Okay. Okay, I could. We could maybe consider this. Nice. Size of the solution plus 3. And the 3 width, yes, it's not. That would be better than the size of the solution plus maximum degree, right? I mean,
Well, yeah.
roughly.
It depends. Like,
Yes. Oh. Okay. Okay. Thank you. I will look into that.
Other ideas what to solve in this afternoon? Other parameters? All right, then thank the speaker again.